Hello, chemists. I am going to walk you through how to do gas law calculations, and there will be a slideshow of notes that you can look at on Google Classroom. You can email me with any questions, but right now, with the state of our circumstances, I'm not going to make it too complicated. Your first page on the assignment is a reference sheet. You do not have to know these gas laws by name. You don't have to know that P1 V1 equals P2 V2 is Boyle's law. That is fine. As long as you know when to use them, that's all I really care about. We will be using Boyle's law, Charles's law, Gay-Lussac's law, the combined gas law. We're going to skip Dalton's law of partial pressure. We will be using the ideal gas law, and we will skip Graham's law. Important reference information down here: standard conditions, STP, standard temperature and pressure, is 0 degrees Celsius, which is 273 Kelvin. We will always be working in Kelvin. Remember that. Standard pressure conditions is 1.00 atmospheres, abbreviated as ATM. And then you have conversions. So 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 76 centimeters of mercury, which is equal to 101.325 kilopascal, which is equal to 101,325 pascal, which is equal to 29.9 inches of mercury. So depending on what unit you are given and what unit you have to use, these conversions will come in handy. The abbreviations are pretty straightforward. Temperature conversions: if you are going from Celsius to Kelvin, you add 273 to your Celsius temperature. If you want to go from Kelvin to Celsius, you just subtract 273. That's easy. Down here in your ideal gas law, N stands for moles. R is a gas constant, and there are a couple different options, and you may be wondering, well, which one do I use? If there are 3 options down here, which one do I need to use? And that depends on the units you are working with. If you have a volume in liters and a pressure in kPa or kilopascal, you would use your 8.31 R value. If you have liters of volume and atmosphere of pressure, you would use your 0.0821 R value. If you have liters of volume, torr, and pressure, you would use 62.4 as your R value. As long as all of your units match up in your formula here, you'll get the right answer using any of these R values. It may require a little bit more conversions depending on which route you take, but you'll end up with the right answer no matter what you do, as long as your numbers are correct and your units match up. So this front page is going to be pretty helpful to you as you work your way through this paper, and you will be skipping numbers 6 and 7. That's it. I made a note of that on Google Classroom. You can skip number 6 and 7. So gas laws. A little tip would be to note the variables as you see them. So in the little paragraph that you have as your question stem, if you see a pressure value, write P1 if it's the first pressure you see. If you see a second pressure, write P2 above it. Annotate. As I had said, R values depend on other units provided, and all temps are in Kelvin. So let's go through a quick example with Boyle's law. So none of these will be labeled for you as being a specific gas law. You will have to figure out what it is as you go along. So a sample of hydrogen gas has a volume of 340 cubic centimeters. Well, there's a V1. And a pressure of 101.9 kPa. So there's a P1. What volume? Oh, there's our V2. would the gas occupy at 81.0 kPa? There's our second pressure, if the temperature remains constant. So, the variables that we have 2 volumes, 2 pressures. If we look at our formula sheet, that aligns with Boyle's law, P1 times V1 equals P2 times V2, and then you just have to plug it into your formula and do a little simple algebra. So multiply these two, divide by that one, and we end up with 430 cubic centimeters as our second volume with 2 sig figs. Sig figs are a thing for this assignment, so I apologize in advance. There are only 2 sig figs there, there are 3 sig figs there, and 4 sig figs there, and we're only allowed to use the lowest number of sig figs since we are multiplying and dividing, so you are going to have to round to 430 for this question. Alright, next up, we will have a Charles's Law example. So 12.01 cubic decimeters, sounds like a volume to me, of fluorine gas is collected at 56.6 degrees Celsius, sounds like a temperature to me. What volume? There's our second volume. Would the sample occupy at negative 40.5 degrees Celsius? There's our second temperature, if the pressure remains constant. So, going through, annotating, keeping track, the variables we have are 2 volumes, 2 temperatures. Looking at our formula sheet, V1 over T1 equals V2 over T2. That would be Charles's Law. And then, it's just a matter of plugging it into the formula, cross multiply and divide, and sig figs, we would end up with 8.47 cubic decimeter. So whatever unit you start with will be the unit you end with. So far everything's pretty straightforward and easy. You'll probably start off kind of slow as you're labeling all the variables and trying to figure out which one goes where and what formula to use, but you should catch on pretty quickly. All temperatures are in Kelvin, so we have to add 273 to our Celsius values that we were given. Other than that, it's pretty easy. 3 sig figs, 3 sig figs, 4 sig figs, so we will end up with 3 sig figs in our final answer. Okay, on to the next one. Our next question will be using the Gay-Lussac's law, and our question stem here. A sample of gas in a closed cylinder is heated from 20.5 degrees Celsius, that's a temperature, to 51.0 degrees Celsius, that is another temperature. If the initial pressure, there's a pressure, it's 1.75 atmospheres, what is the final pressure? Second pressure. So as we are reading through this and keeping track of the variables, we have 2 temperatures, 2 pressures, and that would tell us that we are dealing with Gay-Lussac's law, P1 over T1 equals P2 over T2. Temperatures are in Kelvin as always, so you'll have to convert as you plug those in, and we end up with 1.75 atmosphere over 293.5 Kelvin is equal to the second pressure over 324 Kelvin, cross multiply and divide, and our final answer would be 1.93 atmosphere with 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, that's easy. Next up, the combined gas law. So a sample of gas has a volume of 225 cubic centimeters at 25.2 degrees Celsius and 56.5 kPa. What volume will the gas occupy at standard temperature and pressure? And we talked about what standard temperature and pressure meant when we were going over our reference sheet. Standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, since we are using Kelvin in these calculations, and 1.00 atmospheres. all of our variables, we have 2 pressures, 2 volumes, 2 temperatures, and that would tell you that you are going to be using the combined gas law. Now all you have to do is plug all of those values in there. So our first pressure is 56.5 kPa. First volume is our 225 cubic centimeters, and the first temperature is going to be 298.2 Kelvin, since we convert from Celsius to Kelvin. And then our second pressure will be 101.325 kPa. You could have done this 2 ways. You could convert that to atmospheres and use 1.00 atmospheres over here. But instead, since we have that reference sheet with the conversions, I just took the standard pressure of 1.00 atmosphere, which is equivalent to 101.325 kPa, and plugged it in there. If you put 1 atmosphere here, you would have to convert 56.5 kPa to atmospheres. So I thought this was easier that way, since I already have it on my reference sheet. But as long as your pressure values, your units are the same, everything will work out fine. And then our second volume is what we're going to be solving for, and then the standard temperature of 0 degrees Celsius and 273 Kelvin will go in there. You can solve for this side. Make sure that you use all your decimal points for your intermediate calculations, and then if you divide 101.325 by 273, you end up with that long number, still multiplied by your second volume. Divide both sides by this value to get V2 all alone, and with 3 sig figs we have 115 cubic centimeters. So that one was a little bit more work than the others, and we are almost done. So last but not least, we have the ideal gas law. And a nice thing about the ideal gas law is that if you are given a value in moles or grams of an element, you should automatically think ideal gas law. So at what temperature? There's a temperature. Well, 13.5 grams of molecular nitrogen, you should be thinking moles, so you're going to have to convert that to moles, exerts a pressure of 2,120 millimeters of mercury in an 8.5 liter cylinder. So we have P, V, N, R is the constant, and T. So we will be using the ideal gas law. PV equals nRT. There's a song about it on YouTube if you want to look it up. It might be by the same guy that does the Mendeleev song. It's Bob. So, looking at all of our variables, we have everything we need with our gas constant R to use the ideal gas law. First thing you'll have to do, this is kind of a labor-intensive question. You need to convert millimeters of mercury to a unit associated with an R value. I'm choosing atmospheres. You could do kPa, atmosphere, or torr. I'm an atmosphere kind of guy, so I'm going to do that. So using our conversion factor of 760 millimeters of mercury is equal to 1 atm. Dimensional analysis, it's back, never really went anywhere. So we have 2,120 millimeters of mercury, 760 millimeters of mercury equal to 1 atmosphere. Take that divided by that, and we have 2.79 atmospheres of pressure. Next up, we need to convert the grams of N2 nitrogen to moles of N2 nitrogen. So we have a 13.5 gram sample. Diatomic nitrogen has a molar mass of 28.02 grams per 1 mole. units cancel, we end up with 0.481 moles of nitrogen. Now that we have values that we can use, we can throw them into our formula. So the ideal gas law: P, pressure, 2.79 atmospheres, V, volume, 8.5 liters, equals N, 0.481 moles, R, which is our gas constant, and with the atmosphere unit, it will be 0.0821, and you get that off of your gas law equation symbol sheet. And then temperature is what we will be solving for, and every temperature that you get as an output in this calculation will be in Kelvin, and we were asked what temperature Celsius, so we're going to have to go back and convert once we get our answer. So we can multiply the 2.79 by the 8.5 and get that number. And remember to keep all decimal points and wait to round until you have a final answer at the end. We can multiply these two numbers, and then we will have to divide by that number to get our temperature all by itself. And our temperature in Kelvin, without rounding or taking any decimal places off of it, 600.5302595, and we can subtract 273 to convert to from Kelvin to Celsius, and then with only 2 sig figs, because our volume is 8.5 liters, we can only use 2 sig figs. We have to round that to 330 degrees Celsius. So that is all you need to know, all you will have to be able to do for your gas laws assignment. As long as you annotate and keep track of what variables you have, the variables you have and the variables you are asked for will lead you to one of these 5 equations. So if you have any questions, let me know. Send me an email and I'll get back to you. Take care.